All right, normally we space tick marks along the x-axis and the y-axis 1 unit apart, but there's nothing sacred about that. For instance, we could have tick marks spaced 100 units apart on the x-axis and maybe 500 units apart on the y-axis. It depends what kind of application you're subjecting this coordinate system to. But the key is that both these axes nonetheless have to be linear axes. So if 2 tick marks are 1 unit apart, then all tick marks have to be 1 unit apart. If 2 tick marks are spaced by 1,000 units apart, then all tick marks have to be spaced 1,000 units apart. Okay. These 2 axes take my plane or my paper and partition it up into 4 different planes or 4 different quadrants. Quadrant number
a pencil that waters.
Quadrant number 1 is bounded below by the positive x-axis and bounded to the left by the positive y-axis. Quadrant number 2 is bounded below by the negative x-axis and bounded to the right by the positive y-axis. Quadrant number 3 is bounded above by the negative x-axis and bounded to the right by the negative y-axis. And quadrant number 4 is bounded above by the positive x-axis and bounded to the left by the negative y-axis. The point of intersection between the x and y axes is a very special point. It's called the origin. Okay. And this construction has a lot of different names. Sometimes we just call it the plane or the XY plane, or sometimes it's called rectangular coordinate plane, or even the Cartesian coordinate plane. So it has a lot of different synonymous names. Okay. Any questions about this construction here? Notice if you go to the right on the x-axis, you're moving in a positive direction. If you go to the left, you're moving in a negative x direction. If you go upwards on the vertical axis, you're moving in a positive y direction. And if you go downwards on the y-axis, you're moving in a negative y direction. First of all, what are we going to do? We're going to learn how to plot what are called ordered pairs or points in the xy plane. Ordered pairs look like this. Parentheses basically enclose the coordinates of the ordered pair. The first entry is called the x-coordinate of the ordered pair. The second entry is referred to as the y-coordinate of the ordered pair. Together, these coordinates and collectively this point has a unique location in the xy plane. For instance, if we wanted to plot the ordered pair 2, 5, we would start at the origin, and then we would move 2 units to the right on the x-axis, and then we move up 5 units parallel to the y-axis. And there is the location of the unique point 2, 5, and it happens to be located in the first quadrant. Any questions how we plotted the ordered pair 2, 5? All right, to plot this other ordered pair, -5, -4, we start at the origin and we move 5 units to the left on the x-axis since my x-coordinate is -5. And then we move down 4 units parallel to the y-axis since my y-coordinate is -4. So 5 to the left, down 4, and you have the point -5, 4, which is right here in the third quadrant of the xy plane. Any questions how we're plotting points in the xy plane here? All right, we good on that? All right, so let's have some fun and plot some other points here. 5, -3. Notice 5, -3 is found in the fourth quadrant. We start at the origin, we move 5 to the right on the x-axis, and we move down 3 units in the negative y direction parallel to the y-axis. And then we locate the point 5, -3. 0, 4, we start at the origin. We do not move right or left on the x-axis since our x-coordinate is 0. We just move up 4 units along the y-axis. So therefore 0, 4 is found right there. It happens to lie on the y-axis. It does not lie in any quadrant. -3, -2, starting at the origin, I move 3 units to the left on the x-axis. And then I move down 2 units parallel to my y-axis. And we locate the point -3, -2, which lies in the third quadrant. Any questions how we're plotting these points here? -2, 0, we start at the origin, we move 2 to the left on the x-axis, and we stay on the x-axis since our y-coordinate is 0. Negative 2, 0 is this point that lies on the x-axis. Finally, 2, 6, we start at the origin, we move 2 to the right on the x-axis, and then we move up 6 units parallel to the y-axis, and therefore we locate the point 2, 6, which lies in the first quadrant. Any questions, ladies and gentlemen, how we're plotting ordered pairs here? Now, some ordered pairs might not have real nice x and y coordinates. Some of them could be a little messy. For instance, if I had the ordered pair 3.5, let's say 2 3/4, how would we plot this point? Well, we're basically, accuracy is basically limits us to the fact that these tick marks are spaced 1 unit apart. So we just have to do the best we can. So 3.5, we start at the origin, we move 3 and then a half more along the x-axis. And then I got to move up 2 and then 3/4 more. 3/4 more might be like right about here. So that would be the approximate location of that point, 3.5, 2 3/4. So you just have to do the best you can when you have fractional or decimal coordinates. Okay. All right, any questions? How we are plotting points in the XY plane?
Can you show the fraction, how you plot the fraction again?
Well, if we have a, let's say we want to try to plot negative 6, 6.5, and negative 4 and like 1/4 or something like that. So I start at the origin, I have to move 6.5 units in the negative y, on the negative x direction rather. So we move 6 units to the left on the x-axis, and we got to move a negative 1/2 more unit to the left. So right there, there's negative 6.5. Now we got to move down negative 4.25, parallel to my y-axis. So there's negative 1, negative 2, negative 3, negative 4, and then I got to move down 1/4 more. So like right about there. You just approximate it the best you can. Make sense?
Yeah.
All right. Yeah, we just got to do the best we can with fractional and decimal coordinates. All right. If I plot a point in the XY plane, would you be able to identify its X and Y coordinate address? If you look at point C here, to identify its X coordinate, you project it vertically down to the X axis. And we discover that it hits what tick mark? It hits negative 3. So its X coordinate is negative 3. To determine the Y coordinate of this point, we project it horizontally back to the Y axis. And note the tick mark we strike, which is positive 4. Hence, point C has the ordered pair address of negative 3, 4. Does that make sense there? All right, so what if I plot a point right here? Let's see. All right, what would, hold on a second, it's too big. What if I plot a point right here? What would be its X and Y coordinates? What's its X coordinate?
X would be 4 and Y would be 6.
That's correct. So we have the 0.46 plotted. Is this making sense here? Project this straight down to the x-axis. You strike the 4th tick mark. That's its X coordinate. Projected horizontally back to the Y-axis. You strike the 6th tick mark. That's its Y coordinate. 4, 6. Okay. What point would this be down here? What would be the X and Y coordinates of this point?
Negative
X0, Y,
Zero
negative
and
6.
Y negative 6.
0, negative 6.
Exactly. The X coordinate would be 0 because if you project this, straight up to the x-axis, you hit the 0th tick mark here. Okay, so 0. And as far as the Y coordinate is concerned, the point is literally sitting on its Y coordinate. It's sitting on negative 6. So 0, negative 6 would be the location of that point on the Y-axis there. All right. All right. So again, ladies and gentlemen, we good on plotting points in the XY plane? All right.
Yeah.
Let's see if we can move on now and have a little bit more fun. All right, and this is just more practice here, identifying coordinates of plotted points in the XY plane. You can look at that, just more practice, just re-emphasizing things we already talked about there. Okay. All right. Now, earlier we found out that our two axes divide our coordinate plane into 4 quadrants. And let's see if we can fill in these blanks here. If both coordinates of an ordered pair or a point are positive, the point would have to be in what quadrant? What quadrant do you think, Liz? I'm going to have both the X and Y coordinates are positive. What do you think?
1.
Quadrant number 1, exactly. So this would be quadrant 1, and we denote it by saying Q Roman numeral 1. If both coordinates are negative, where would be B? If both X and Y coordinates are negative,
Quadrant 3.
we'd be down here in quadrant number 3. Okay, so that would put us in quadrant 3, Q and Roman numeral 3. If the X coordinate is positive and the Y coordinate is negative, the point would have to be in what quadrant? X coordinate's positive, but the Y coordinate is what? Negative. So we're
4.
yep, the 4th quadrant. All right. Hold on a second. Wait a minute. We'd be in the 4th quadrant. Okay. Quadrant number 4. All right. Finally, and so that's Q with a Roman numeral 4. If the Y coordinate is positive and the X coordinate is negative, we would find ourselves in what quadrant?
2.
Quadrant number 2. Okay. All right. So do we understand, ladies and gentlemen, the signs of our coordinates for points in the various quadrants here? Okay. Again, the way it works is this: in quadrant 1, both the X and the Y coordinates are positive. In quadrant 2, the X coordinate is negative, but the Y coordinate is positive. Quadrant number 3 down here, both the X and the Y coordinates are negative. And the 4th quadrant, the X coordinate is positive, the Y coordinate is negative. All right. You can just determine the sign of the quadrant if you just project, either up or down and hit the X coordinate and see whether it's positive or negative, or project it to the right or left and hit the Y coordinate and see if you strike a negative or positive number. Okay. All right, done with that. All right, that's just a solution of what we just did. Okay, the next thing we're going to ramp up to, as long as we raise the bar, is we're going to learn how to work with what are called linear equations in 2 variables. And this is in general what a linear equation in 2 variables looks like. A, B, and C are just real numbers where X and Y are the variables. We call this a linear equation because both the variables X and Y are raised to the 1st power. If you stay in this math business long enough, you'll start working with nonlinear equations, where maybe X is raised to the 2nd power or the 3rd power, or maybe Y is raised to the 2nd power or 3rd power. But today we're just going to work with what are called linear relationships or linear equations in 2 variables X and Y. Okay, so let's look at the specific example. Suppose we have this linear equation, y equals 2x plus 6. We could always, rearrange this equation by doing simple algebra on it. For instance, we could get this equation in what is called standard form. And so I want to show you what that form is here. So when we have a linear equation, anytime your equation is written in this form here, ax plus by equals c, where a, b, and c are real numbers, we call this standard form for a linear equation. Any linear equation that's in this form is said to be in standard form. Okay, standard form. And so if I have y is equal to 2x minus plus 6, how would I get this equation into standard form? Well, in order to do that, I need to get x on the same side of my equation with y. How do I move a positive 2x to the left side of my equation?
Subtract.
So we will have to minus 2x from the left, and we're going to minus 2x from the right. This step is showing that. The 2x's on the right drop out, and we're left with y minus 2x is equal to 6. Rearranging these terms to get it into the strict form of ax plus by equals c form, I have negative 2x plus y equals 6. This we now say is in standard form. Okay. Any questions how I went from the present form I had, y equals 2x plus 6, to standard form for that linear equation, negative 2x plus y equals 6.
Can you do it again, please?
Well, I got to get x on the same side of the equation with y. You see that? Because notice, to be in standard form, x and y have to be on the same side of the equal sign.
Okay.
So to move a positive term to the other side of my equation, I have to do what? What's the inverse of addition?
Subtraction.
I have to subtract 2x from both sides. Okay.
Okay.
And when I do that, the 2x's on the right drop out to 0, leaving you with just plus 6. And on the left side, we have y minus 2x, and it's equal to 6. To force it in strict standard form, I want my x term to precede my y term. So therefore, I just rearrange these terms, just flip them around, and you got your answer. Make sense there? I got that in standard form?
Yes, thank you.
All right, so we call that standard form for a linear equation. All right. Now, suppose we choose a pair of numbers to substitute into the equation for x and y, and we basically investigate whether the resultant equation is true or false. So in other words, ladies and gentlemen, I'm going to take this linear equation here in x and y, and I'm going to ask myself this question. Is 414 a solution for this equation? Notice, solutions to a linear equation in x and y have to be ordered pairs, okay? Such that when we substitute the x coordinate in and the y coordinate in, we must get a true statement if the ordered pair is a solution to the linear equation. If after substituting the x coordinate value in and the y coordinate value in, we do not get a true statement, then the ordered pair is not a solution to the linear equation. Let's see if 414 is a solution to this linear equation. So my x coordinate is 4, my y coordinate is 14. I'm going to take 4, substitute it in place of the x variable into my equation, in which case I'll now have negative 2 times 4, plus y is replaced with the y coordinate of 14. And we ask ourselves, does the left side equal 6? Is this true or false? Well, according to the order of operations, we multiply before we add. Negative 2 times 4 is negative 8. Is negative 8 plus 14 equal to 6? Is that true? Well, negative 8 plus 14 is 6. And notice it does check out. And so, ladies and gentlemen, we would conclude that 414 is an ordered pair solution to this linear equation. The answer is yes. So that is a ordered pair solution to that linear equation. It satisfies the linear equation. Do we all understand what just happened there? All right. Do you think all ordered pairs are solutions to any ordered pair is a solution to this linear equation?
No.
No, it isn't. Maybe try this one. Is negative 10 5 a solution to this linear equation? Well, to verify, I replace x with negative 10. So negative 10 goes in for x here, and hence I'll have negative 2 times negative 10 plus y. Y is replaced with the y coordinate of the ordered pair, which is 5. So is negative 2 times negative 10 plus 5, is that equal to 6? Well, let's find out. Negative 2 times negative 10 is a positive 20, and a positive 20 plus 5, is that equal to 6? And obviously, that is not equal to 6. So the answer is no. Negative 10, 5 is not a solution to that linear equation. It does not satisfy the equation. All right, does that make sense there? What we're doing here? We're just verifying whether an ordered pair is a solution to this linear equation here. We found one to be, we found another one not to be. I have a question. This is a pretty deep question at this point in time for this lecture, but I'm going to throw this little challenge question out. Can you think of another ordered pair that would be a solution to this linear equation? Can you think of one that would work in addition to 414? Any other ordered pair that might work for this linear equation, might be a solution. Let's try one here. I'll throw one out here. Is 0, 6 a solution? Replace the x coordinate with the x variable with the x coordinate of 0. 0 goes in for x. And the y variable takes on the value of the y coordinate. So 6 goes in for y. Is this equal to 6? Negative 2 times 0 is 0. Is 0 plus 6 equal to 6? Does this work? Looks like it checks out, doesn't it? So the answer is yes. I found another ordered pair solution, 0, 6. So we found two of them, 414 and 0, 6. Do you think that's it? Or can maybe you think of another ordered pair that might be a solution to this linear equation? Found two of them.
I wrote down -3 and 0.
Okay. Is -3, 0 a solution? Let's find out. Replace the x variable with the x coordinate of -3. -3 goes in here, so I have -2 times -3 plus the y coordinate, which is 0. Is this equal to 6? Does it work? Well, -2 times -3 is 6. Is 6 plus 0 equal to 6? And the answer is yes. We found yet another ordered pair solution, which is -3, 0. So we found three ordered pair solutions, 414, 0, 6, and -3, 0. Do you think that's it? Or is there any other ordered pair solution to this linear equation? And if so, how many ordered pairs do you think would be solutions to this linear equation? Anybody want to weigh in on this?
I'm going to say infinite.
Yep. As it turns out, ladies and gentlemen, we just found three among an infinite number of ordered pair solutions to this linear equation. Infinite number. We'd be here to the end of time or death, whatever grabs us first, and in enumerating all the ordered pair solutions to this linear equation. You know, there's even messy ordered pair solutions. We just named some nice ones with nice integer coordinates. Here's a messier ordered pair solution to this linear equation. It would be like -1/2. -1/2 5, ladies and gentlemen, would be an ordered pair solution to this linear equation. It does check out because if you replace x with -1/2, -2 times -1/2 plus 5 is equal to, now -2 times its reciprocal -1/2 is 1, and 1 plus 5 is 6. It checks out. This is also an ordered pair solution. So ordered pair solutions don't always have to be nice. Sometimes they're a real mess. In fact, there's an infinite number of ordered pair solutions to this linear equation, some of which are nice, but some of which have very, very messy decimals and fractional coordinates. But there's an infinite number of ordered pair solutions to that linear equation. Okay. In fact, ladies and gentlemen, what we're going to do here is we're going to plot the ordered pair solutions that we have found for this linear equation y equals 2x. We're literally going to plot them. 0, 6 we found was an ordered pair solution. 1, 8, believe it or not, is an ordered pair solution. 2, 10 is an ordered pair solution. 3, 12, 4, 14. We also found 0, 6 was an ordered pair solution. We discovered that. -3, 0 would be an ordered pair solution. We've already discovered that. So if you were to project this line further down here to the left, let's see if I can do that. Hold on a second. See if I got my line here. Okay, maybe I can do this. If I was to project this line further down here to the left, it would go through the x-axis at what? At -3? Do you agree we discovered at 0, -3, or I'm sorry, -3, 0 is a solution to that linear equation? Okay. So any point that lies on this blue line, ladies and gentlemen, would be a solution to this linear equation. And notice this line goes in both directions forever. That's what the arrows indicate. So now you can begin to see why there's an infinite number of ordered pair solutions for y equals 2x plus 6. As long as the point lies on the line, we say it's a solution to this linear equation. This line represents what is called the graph of the linear equation. Okay, so the graph of a linear equation is basically going to be in the plane a line that contains all ordered pair solutions to the linear equation. And you can see that some ordered pairs would have very messy x and y coordinates. For instance, this point right here, it would be very difficult to read off its x and y coordinates. It'd be like a messy decimal or fractional value for the x and y coordinates. Here's another one that would have a very messy x and y coordinate. Virtually impossible to read it off with 100% accuracy based on the fact that our scales are having our tick marks spaced 1 unit apart. That's the best accuracy we have at our disposal here. But there's an infinite swath of ordered pairs with messy decimal, fractional, and nice integer x and y coordinates. Okay. All right. And so again, to visually indicate all the ordered pair solutions to a linear equation in 2 unknowns, we don't sit and list them all because, like I said, we'll be here till the end of time listing all of them. There's an infinite number of them. So the best we can do is graph the linear equation by basically plotting a couple of ordered pair solutions and then connecting the points with a straight line. That line represents the set of all ordered pair solutions to a linear equation. Okay. Now, I have a question for you. In general, the graph of any linear equation in 2 unknowns is always going to be a line graph in the xy plane. It's never going to be like, some sort of like a curve graph. Okay, none of this stuff goes on with a linear equation, all right? Because in the word linear is embedded the word line here. See the word line? That's not there for that's not just there for coincidental purposes. That's there for a reason. Because linear relationships between x and y, where both x and y are raised to the first power, always carve out a straight line graph for its solution set. Okay. All right. And this is just reemphasizing what I just said. The graph of a linear equation basically is a visual manifestation of its solution set of all infinite ordered pairs solutions of points that actually lie on the graph. Okay, so I have a question for you. Would this point here be a solution to that linear equation y equals 2x plus 6? Is this point a solution? You think that point's a solution?
Yes.
No,
All right, the answer is no. Why? How do we know that it's not a solution to y equals 2x plus 6?
because it's not in line with the other
That's right,
points.
because it does not lie on the graph, ladies and gentlemen. This point does not lie on this line graph of y equals 2x plus 6. That's why it's not a solution to y equals 2x plus 6. Not a solution. To be a solution, it has to be a point on the line, on the graph. So would this point here be a solution to that linear equation, whatever it is? I don't really care what it is. Is it a solution?
Yes.
It is a solution. It lies on the graph. Okay. Okay. All right, so here we go. We have another one now to play around with, another linear equation, 1x. And by the way, if you just see x, it's understood that it's 1x. 1x plus 2y equals 5. I have a question. Bare minimum, how many points must I, or ordered pair solutions must I plot to determine the unique line graph of a linear equation?
2.
2. That's good enough. If you find and plot just 2 ordered pair solutions to a linear equation, that's good enough to determine its unique graph. Because through any 2 points, we can always put a unique line. Okay. Now, if you just plot 1 point or 1 ordered pair solution to a linear equation, that's not good enough. Because through 1 point, you could actually put an infinite number of lines. Infinite number of lines through 1 point. So you need to plot at least 2 ordered pair solutions to a linear equation to uniquely determine its graph. But you know what? With 2 points, sometimes we can get into trouble if we're really sloppy. For instance, here's how we could get into trouble. If we're not careful, ladies and gentlemen, we could get into trouble if we do not have our line going right through the dead center of the 2 point or ordered pair solutions to a linear equation. We could have our line graph this way, or we could be just as sloppy and maybe graph it this way. Do you agree that these lines do not look like the same line here? Looks like they have radically different slopes or slants to them. You see that? Because I was very sloppy in putting my line through these 2 ordered pair solutions. So if you do plot bare minimum 2 points, just be careful. Make sure you put the line literally through the center of the points, both points. And then you should be okay. If you're not confident in your ability to do that, then I would recommend that you plot maybe a 3rd point, because that will help you to uniquely and accurately graph the linear equation. So 2 points are bare minimum good enough, but 3 points are actually what? A little better. Okay. All right. So let's try this out here. How would we graph x plus 2y equals 5? Well, we need to come up with at least 2 unique ordered pair solutions to this linear equation in order to graph this. Now, to do this, what you can do is you can choose some nice values for x. In reality, it doesn't matter what number you choose for x. Y will have to depend upon it according to the equation that embodies this relationship between x and y. For that reason, you might want to choose some nice values of x. In other words, you don't want to choose like x is equal to 1,000. Good luck in plotting that point. Do you agree? Can you imagine trying to plot a point with an x coordinate of 1,000? That's not happening. So don't do this. Choose some nice values for x. Kind of keep them close to 0. X equals -1 is a nice choice. Choose maybe x equals +1. That's a good choice. And maybe x equals 5. All these are nice choices here. So when x is -1 or 1 or 5, let's find out what y would be in order to generate 3 unique ordered pair solutions to this linear equation. And so here we go. So if x is equal to -1, we're literally going to substitute -1 in for the x variable. And then I'm going to solve for y. I'm going to add 1 to both sides, divide both sides by 2, and I get y must be 3. So, ladies and gentlemen, I found 1 ordered pair solution to this linear equation. It must be -1, 3. Everybody see that there? I generated an ordered pair solution. I put -1 in for x, and I got out 3 for y. Suppose we let x be +1. Put 1 into the equation for x. Solve for y. When we solve for y, we determine we get y is equal to 2. We found another ordered pair solution. 1, 2 is another point that will lie on the graph of x plus 2y equals 5. All right, let's find another one. Let x maybe be 5. Solve for y. We get y is 0. Hence, another ordered pair solution has got to be 5, 0. Everybody understand how we generated these 3 ordered pair solutions to this linear equation x plus 2y equals 5? And there's an infinite number of other ordered pair solutions too. We just found 3 nice ones. Any questions on how we did that? We conveniently just chose some nice values for x, plugged them in for the x variable, and then solved for y to generate these ordered pair solutions. So I have a question for you. Do we have enough information to accurately graph this linear equation in the xy plane?
Yes.
Yes, we do. We have bare minimum 2 points. We have better than 2 points. We have 3 points. So I'll tell you what, let's take these 3 points, plot them in the XY plane, put a line through them, and let's see what the graph would be. And there you go. We plot the 3 ordered pair solutions we found, put a nice straight line through them using a ruler. Oh, by the way, what kind of paper do you think you should use for accuracy when you're working in the XY plane? It has a name. It's called, what kind of paper? It's called,
Graph paper.
Graph
Paper.
paper.
yeah, it's called graphing paper, ladies and gentlemen. And in fact, what I will do, I'll scan one of these and place one of these for your disposal on Canvas, okay? You can print this out and make copies of it, and you'll have some nice graphing paper to work with. All right. Always use graphing paper when you're working in the XY plane for accuracy. The reason being is because these tick marks are all automatically evenly spaced for you on the X and Y axis. If you don't use graphing paper, then good luck, because spacing your tick marks evenly, ladies and gentlemen, on your axes could be a major challenge. Do you agree? You might end up with a real mess like this. All right. Use graphing paper. And again, I'll post one of these on Canvas so you can print this out, do what you want with it. Or you can maybe download some graphing paper for free online. There's many free sites where you can download and print off graphing paper. Or you can go to like an office outlet and just buy a tablet of graphing paper. It's relatively cheap. So I'll leave it up to you. But yeah, please do use graphing paper when you work in the XY plane. All right, and this is very important. Make sure you always put arrows on the end of the line graph, because the line has to go in respective directions forever. That's critical. So we have graphed x plus 2y equals, what was it, 6? Was it? I think it was 6. Yes, it was 6. Okay. Everybody understand how we graph that linear equation? We graph that linear equation by basically just choosing some nice values for x and cranking out some ordered pair solutions. All right, let's move on here. Now, ladies and gentlemen, there's another way we can graph a linear equation. It is by finding what are called intercepts of the linear equation. And your author does a lousy job here in the PowerPoint, so I'm going to go to my overhead by DocCam here and show you what these intercepts are all about here. Okay. Suppose that I have a linear equation and I graph it in the XY plane, and suppose that the graph looks like maybe like this. Okay, so that's the graph of some linear equation. That's its graph. Now, the point where the graph intersects the y-axis, this point has a very special name. It's called the y-intercept of the linear equation, the y-intercept. The point of intersection between the graph and the x-axis is also a very special point. It's called the x-intercept of the linear equation, the x-intercept. Because a y-intercept must always be a point that lies on the y-axis, its x-coordinate always has to be equal to what? What do you think the x-coordinate of a y-intercept must always be equal to? The x-coordinate must always be equal to what for a y-intercept? Must always be equal to 0? Yeah, the x-coordinate of a y-intercept must always be 0. Because if the x-coordinate of a point is not 0, then the point does not lie on the y-axis. It lies to the right or to the left of the y-axis. In a similar fashion, since an x-intercept is a point that always lies on the x-axis, its y-coordinate must always be what? 0. Because if a point's y-coordinate is not equal to 0, then the point does not lie on the x-axis. It would lie either above or below the x-axis. Is this making sense here? So, ladies and gentlemen, in order to find a y-intercept for a linear equation, we always set x equal to 0. In order to find an x-intercept for a linear equation, we always set y equal to 0. Always. That's not just true for linear equations. That's true for all relationships involving x and y, even if they're nonlinear. Make sense? Those are called x and y intercepts. All right. So suppose we have this linear equation, 2x minus 3y equals 6, and we want to find the x and y intercepts for this linear equation. And then we will use the x and y intercepts to ultimately graph this linear equation in the xy plane. Well, to find the x-intercept, we always set what variable equal to 0. You know, an easy way to remember this, ladies and gentlemen, is in order to find an intercept, you set the other variable equal to 0. To find an x-intercept, you set y equal to 0. To find a y-intercept, you set x equal to 0. It always works that way. All right, so to find the x-intercept, we let y be equal to 0. Take 0, substitute it into the equation for the y variable. So 0 drops in right here. Therefore, our equation now looks like this upon making the substitution. 3 times 0 drops out. We're left with 2x equals 6. We can easily solve for x. Divide both sides by 2. We get x equals 3. Hence, our x-intercept for this linear equation is the ordered pair 3, 0. Any questions how we just found the x-intercept for this linear equation by setting y equal to 0? That's the x-intercept for that linear equation. In a similar way, we'll find the y-intercept for this linear equation. To find the y-intercept, what do I set equal to 0 always? I set the x variable equal to 0. So take 0, substitute it in for the x variable into the linear equation. And upon doing that, your equation collapses down to this. 2 times 0 is as good as saying that this term is gone. That's 0. And we're left with this simple linear equation of which we can hopefully now solve for y. To do so, we divide both sides by -3, and 6 divided by -3 will give us our y-intercept, which is -2. Hence, as an ordered pair, your y-intercept is 0, -2. That's your y-intercept. So we found the what? The x-intercept is 3, 0. We found the y-intercept is 0, -2. Questions how we just found the x and y-intercepts for this linear equation here? Question, do I have enough information to graph this linear equation, knowing its x and y-intercepts, and knowing that they are unique points? Should be good enough, do you agree? So I'll tell you what, here's what we're going to do here. We're now going to plot the x and y-intercepts. We plotted 0, -2 on the y-axis here, and then we plotted the x-intercept, which is 3, 0 on the x-axis. Take a ruler, put a nice straight line through the center of both these points, and you have the graph of that linear equation, 2x minus 3y equals 6. Again, make sure you always put arrows on the end of the lines. Arrows on both ends of the line. Any questions, ladies and gentlemen, how I graph this linear equation, 2x minus 3y equals 6, by finding its x and y intercepts and using those points to graph it? That's another popular way of graphing the linear equation, is by finding its x and y intercepts, plotting them, and putting a nice line through them. So we've seen 2 different ways of graphing linear equations. The first way, they normally call the table method in most textbooks, in which we just select nice values for x, plug them in, and solve for y to crank out ordered pair solutions. Plot the ordered pair solutions, put a line through the points, and we have the graph. This is an alternative way of graphing a linear equation called the x-y-intercept method. By computing the x and y intercepts of a linear equation and plotting the 2 points, we can also put a line through them and also graph the linear equation. Just another way. And another reason why we're showing you or exposing you to these intercepts, ladies and gentlemen, is because these intercepts have very, very important meanings in application problems when you start trying to apply linear equations to the real world. All right. Now, the next thing, ladies and gentlemen, we're going to talk about here is called the slope of a line. And your author does a lousy job here on the PowerPoint. So I'll tell you what, bear with me. I'm going to go grab my elementary algebra book and it has a much better visual explanation as to what slope's all about for a line. So hold on here. Here we go. All right. Ladies and gentlemen, we're now going to talk about what's called the slope of a line. All lines in the XY plane have a certain slant to them, okay, or a certain steepness to them. If any of you have ever done any downhill skiing, you know, maybe you'd say to your friend on the weekend, hey, you want to hit the slopes? You know, that's kind of a cool way of saying you're going to go skiing, downhill skiing. Well, in order to do downhill skiing, you have to have some sort of a slope. Do you agree? You're not going to do any downhill skiing on a strip of land that's horizontal. All right, that's not happening. You have to have gravity helping you out a little bit. That only occurs on slopes. So, ladies and gentlemen, the slope of a line in a crude sense is the measure of how steep a line is in the plane. But we like to become more mathematically precise in what we mean when we say how steep a line is in the plane. To do that, what we're going to do is we're going to learn how to compute what is called the ratio of the amount of rise versus the amount of run we experience as we move from one point on our line to some other point. Right? For instance, suppose I plot two unique points on the graph of a linear equation. I plot two unique points on a line. And I label them as the point P sub 1, which has x and y coordinates of x sub 1, y sub 1. This little 1 here is called a subscript. Subscripted variables are used all the time in higher level math and also computer science. We call this x sub 1, y sub 1. Okay. And these are the coordinates of the first point we're plotting or we're choosing on our line, which is called point P sub 1. We choose another point on our line, which is denoted as P sub 2. Its x coordinate is x sub 2, and its y coordinate is y sub 2. Now we need to understand that subscripts must never be confused with powers or exponents. X sub 2 has no relationship whatsoever to x squared. No relationship whatsoever. This is called a subscript. This is called an exponent. Okay? Subscripted variables are used, like I said, usually in a course in computer science because they lend themselves nicely to what are called arrays in computer science, 1 or 2 or 3-dimensional arrays. Okay. All right, so ladies and gentlemen, we have two unique points on a line, and how do we know they're unique? We know they're unique because the subscripts are not the same. Because these subscripts are different, okay, we know that these points are not the same point. They're unique points. All right, suppose I'm a person walking up along this slope here, and I walk from point P sub 1 up to point P sub 2. As I walk along this red sloped line here, I'm going to experience two things changing. I'm going to experience a change in my horizontal position, and I'm also going to experience a change in my vertical position. Two things change simultaneously as I walk from point P sub 1 along this red line up to point P sub 2. I experience a horizontal change and a vertical change. And the ratio of the amount of vertical change I experience to that of the amount of horizontal change I experience is called the amount of rise over run I experience as I move from point P1 to P2. Okay. Any questions about this so far here? And notice, ladies and gentlemen, we have basically built a right triangle here also by denoting a horizontal change and vertical change or run and rise here. We have a right triangle here. Everybody see that there? Okay, let's become more specific. Exactly how much vertical change and horizontal change do we experience as we navigate from point P1 up to P2, or if we walk from P2 down to P1 along this red line? Well, let's become more precise. If I take point P2 and I project it straight down to the x-axis, what tick mark value do I strike down here? What's the x-coordinate of point P2, P sub 2? I strike the tick mark value x sub 2. Am I clear on that? If I take point P1 and project it perpendicularly down to the x-axis, what tick mark value do I strike? What's its x coordinate? X sub 1. True. So the amount of horizontal change I experience as I walk along this red line from point P sub 1 up to P sub 2 is the difference between the x coordinates of these 2 points. X sub 2 minus x sub 1. That's the amount of run or horizontal change I experience. In a similar fashion, if I project point P sub 1 horizontally in a perpendicular fashion back to the y-axis, I strike the tick mark y sub 1. If I project point P sub 2 horizontally back to the y-axis, I strike tick mark y sub 2. The amount of vertical change that I experience in moving from point P sub 1 up to P sub 2 along this red line is the difference between the y coordinates, y sub 2 minus y sub 1. So now we can become more precise in our slope formula that we're trying to develop here. Any questions about this here? So therefore, ladies and gentlemen, we developed the slope formula. So given 2 unique points on a line, x sub 1, y sub 1, and x sub 2, y sub 2, we can compute the slope of that line by using this slope formula here. And notice the slope formula in the numerator has the amount of rise represented as the change or the difference between the y coordinates of these 2 points. And the amount of run, okay, is the denominator of this ratio, which is the difference between the x coordinates of the 2 points. So the change in y over the change in x represents the slope of a line in the xy plane. The slope of a line, ladies and gentlemen, is the rate of change, we say, of the y variable with respect to the x variable. I'm going to say that again, it's so important. The slope of a line is a rate of change of the y variable versus the x variable. There's a lot of rates in our everyday lives. We get in our car and we drive 30 miles per hour. That's called a rate. Rate of change of distance versus time. You get on your computer keyboard and you type 40 words per minute. That's a rate. That's the rate with which you type words per time, okay? So slope is really a rate of change of one variable with respect to another variable. So that's the slope formula. That's the formula you want to memorize. They use M in all textbooks for slope. Why? I looked it up once, but it still doesn't make any sense in my mind why. But ladies and gentlemen, they just use M for slope always, okay? That's just the letter they use to represent the slope of a line. All right, hey, let's try this out. Suppose we want to compute the slope of the line that contains these 2 points, 1, 2, and 3, 5. How could we do that? Well, we have to label these points. Now, doesn't matter which point you designate as being point 1 and point 2. The answer is absolutely not. It doesn't matter. Suppose I designate 1, 2 to be my point x sub 1, y sub 1, and I call my point 3, 5 the ordered pair x sub 2, y sub 2. To compute the slope of the line that contains these 2 points, we will use the slope formula. So in for y sub 2, I substitute what? 5. In for y sub 1, I substitute 2. In for x sub 2, I substitute 3. In for x sub 1, I substitute 1. Hence, the slope is going to be 5 minus 2 over 3 minus 1, which gives me a slope for this line of being 3/2. 3 over 2. Any questions how, using that slope formula and these 2 points on my line, I computed the slope of that line? Hey, why don't we plot these points, put a line through them, and look at the graph, see what the slope is really saying in a geometric interpretation here. Well, there's the 2 points. We plotted them, put a line through the points, and the slope of this line is 3/2. What this is really saying is this. If you were to walk along this red line from the point 1, 2 up to the point 3, 5, you would experience a rise of 3 positive units. And you would experience a run of 2 positive units. So the ratio of the vertical change versus horizontal change, or the rise to the run, would be 3 over 2. That's why the slope of this line is 3 over 2. Remember, ladies and gentlemen, I said it doesn't really matter which point you call your first and second point here. For instance, what if I designated my first point? What if I called my first point 3, 5? And I designated my second point as 1, 2. Would I get the same slope? The answer is absolutely yes. It doesn't matter which point you call your first and second point. And to convince ourselves, let's try it out again. So slope of a line is equal to y2 minus y1 over x2 minus x1. So therefore, in for y2, based on how I label these points, I'll put 2 in. That's my y coordinate of my point. Wait a minute here. Hold on a second. This should be the point x sub 2, y sub 2. Sorry about that. There you go. So in for y sub 2 goes 2. Subtract y sub 1 is 5. And that sits over x sub 2, which is 1, minus x sub 1, which is 3. And what I get in this case is I get -3 over -2. But I got a question for you, ladies and gentlemen. Isn't -3 over -2 the same thing as what? What is this really equal to? This is also equal to what? Positive 3/2? Isn't that true? So look at, it doesn't matter whether we walk from 0.12 up to 0.35 or walk from 3.5 down to 0.12 along this red line. If I walk from 0.35 down to 1.2, my rise would be now in the negative y direction of -3 units. -3 units is the rise. And the run would be not in the positive x direction, but the negative x direction, -2. Same slope. -3 divided by -2 is the same thing as +3 divided by +2. So whether you walk down from 0.35 to 1.2 or up from 0.12 up to 3.5, your slope will be the same. So whether you call the slope +3 over +2 or call it -3 over -2, same slope, same line. Is this making sense here? All right, let's get back to that PowerPoint and see if they have anything to offer. All right, this is a well-known fact, ladies and gentlemen. Just by looking at the orientation of the way your linear equations graph is in the XY plane, you can tell whether the slope is positive, negative, 0, or undefined. If your line is oriented this way, we call this a rising line. Rising line. We call it a rising line because as you progress from left to right in the plane, the y coordinates increase in value. We rise on the line, okay? Rising lines always have positive slopes, always. So whenever you graph a linear equation and this graph looks like that or is oriented that way in the plane, its slope had better be positive. If it's not, you made a mistake. This is called a falling line. Any line that's oriented this way is called a falling line. And falling lines are lines basically are lines whereby if we move from left to right in the plane, we're falling down on the line. Falling lines always have negative slopes. So the slope of a falling line is always less than 0, which means it's always negative. There's two other scenarios. If we have a vertical line in the XY plane, its slope is always undefined. Undefined. The reason being is because on a vertical line, if you choose 2 unique points on a vertical line, and if you walk from one point along the one point to the other point on the vertical line, is its x-coordinate changing? Notice its x-coordinate doesn't change, only its y-coordinate changes. So in the slope formula, if you use 2 unique points on a vertical line and you try to put the coordinate values into the slope formula, you're going to discover that because the x-coordinates of these 2 different points are the same, the denominator is going to become 0. And what happens when you try to divide something by 0? Is that defined? It's undefined. And that's why vertical lines always have undefined slopes. Contrast that with a horizontal line. If the graph of a linear equation is a horizontal line, then the slope of a horizontal line is always 0. And the reason why it's 0 is because the reason why it's 0 is because if you move from one point to another point on a horizontal line, there's no rise. There's no change in your vertical location. It's just always a horizontal change or just run. And therefore, there is no rise. So the difference between the y coordinates of these 2 points lying on a horizontal line is going to be 0. And 0 divided by any non-zero real number is always 0, which is defined. It's 0. So horizontal lines have 0 slope. Any questions? Just by looking at the orientation of the line that you graph from a linear equation, you can determine whether its slope is positive, negative, undefined, or 0. It's got to be one of those 4. All right, here's an example. Given 2 points on a line, we want to compute the slope of this line. So we would use our slope formula. Suppose we call 2, 3 the first point and 5, 8 the second point, feeding in the values into the slope formula. And for y2 goes what? 8 minus y1. Y1 is 3. That's the amount of rise or the amount of change in the y coordinate you experience, or the amount of vertical change, divided by the amount of run, which is x sub 2. X sub 2 is 5. Minus x sub 1. X sub 1 is 2. So the slope of this line would be 5/3. So I got a question for you. If I was to plot these 2 points in the xy plane, would this be a rising line, falling line, vertical line, or horizontal line? What would be the case? What kind of a line would it be?
Positive
Rising.
slope.
It would be
Rising.
a rising line, yes, because it has a positive slope. So if you were to plot these 2 points, put a line through them, you better expect that line to have this orientation in the plane. Better be, because it has a positive slope. And if it doesn't, a mistake's made somewhere. All right, so that's a rising line that contains those 2 points. All right, now here, ladies and gentlemen, they want us to find the slope of the line whose equation is given to us in standard form, 5x minus 3y equals 15. To do that, it would probably be easiest to generate 2 ordered pair solutions for this and then put those into the slope formula to crank out the slope. Easiest way to generate 2 ordered pair solutions for this linear equation is to find its x and y intercepts. So how would we find the x-intercept? I would set what? What equal to 0 to find an x-intercept? I would set y equal to 0. Take 0, substitute it in for the y variable, and this term drops out. Then you can solve for x. Divide both sides by 5, and you get the x-intercept is 3, 0. To find the y-intercept, on the other hand, we set x equal to 0. Take 0, substitute it in for the x variable. And when you do that, this term drops out. And then you can solve the equation for y. By dividing both sides by -3, we get the y-intercept is 0, -5. We got 2 unique points. We should be able to put these into the slope formula to determine the slope of this line. It looks like they called this the second point, and they designated this point as being the first point. Again, it doesn't matter which one you call first and second point. Anyways, therefore, y2 would be -5, subtract y1 would be 0, over x2 would be 0, subtract x1 would be 3, and we get the slope is -5 over -3, which is equivalent to saying the slope is positive 5/3. See that there? Positive 5/3. So if you were to take the time to graph this linear equation by plotting its intercepts, putting a line through the points, you would expect the line to be a rising line. All right.
Over the X, up, under the 5,
Yep.
you had, oh, well, you erased it. I was going off of what you had up there, but that's okay.
Well, did you see how we found the intercepts? 3, 0, and 0, -5.
Yeah, it's just that when you had it up there by the solution, I didn't know what that was, if it was a N or a plus.
Okay, I apologize. I erased it a little bit quick there. All right, and for Y2, they called this the second point. Okay. And they designated this as being the first point on the line. So in for Y sub 2 would go what? -5? That drops in right there. Wait a minute. Wrong place. Wrong place. So in for Y sub 2, -5 goes in what? Right here. There you go. In for Y sub 1 would go what? 0. Drops in there. In for X sub 2 would go what? 0. And in for X sub 1 would go 3. Do you see how they're making the substitutions here?
Yes.
And then they go through the arithmetic and then, crank this out. Hey, be very careful when you're using the slope formula with signs. Sign mistakes are very common. Be careful with your minus and your negatives, all right? So yeah, the slope would be -5 over -3, which is +5/3. All right, I don't know, does that answer your question? I apologize.
Yes, thank you.
Whatever that was. Okay. All right, can I get rid of this now? Move on here.
Yes.
All right. All right, now, ladies and gentlemen, there is another very important form for a linear equation. Remember, we said this form was what? What was this form for a linear equation? Remember the name for this?
The standard form.
It was called standard form. You know what? If I take this linear equation in standard form, and if I solve it for the variable y in terms of x, we can hammer this linear equation into another extremely important form. It's this form right here. Y equal to mx plus b form. This is called slope-intercept form. It's a very popular form for a linear equation. Slope-intercept form here. They call it slope-intercept form because from the equation, you can read off the slope. The slope is literally this number m that's being multiplied by x. That is the slope of your line. They call it slope-intercept form because this is a slope, and this number b here, they use b in most textbooks, not all of them, but most. This number b here is called the y-intercept of the linear equation or the line. It's where the line is going to go through the y-axis at. That's why they call this slope-intercept form for a linear equation. Okay? That's a very popular form for a linear equation, slope-intercept form. So check this out. Notice this equation here, 5x minus 3y equals 15 is in what standard form? They want us to put this into slope-intercept form. They want us to go from standard form to the form y equals mx plus b form. To do that, we have to solve this equation for y. So how do we solve for y? Well, the first thing we're going to have to do, and they're leaving a little step out here, is we're going to have to subtract what from both sides? Yeah, you got to subtract 5x from both sides of your equation. 5x's drop on the left, leaving you with -3y equal to -5x plus 15 on the right. Dividing both sides by -3, and they left this step out too. So we're going to divide both sides of our equation by -3. Now notice you got to divide the whole right side by -3. And they're not showing that on the PowerPoint here. You got to divide the whole right side by -3. The -3's on the left cancel, leaving you with y. And look at on the right side, I can split this up. I can put the -5 over the -3. It's legal to do this. -5 over -3 times x plus, and then I can put the 15 over the -3. It's legal to split this up like this. Hey, what's another name for -5 over -3? Do you agree it's positive 5/3? What's another name for -5 divided by -3? -5. Is that true? So, ladies and gentlemen, do we all see how I went from standard form to what form? What form is this? slope intercept form. So what would be the slope of this line? 5/3 is the slope. And what's the y-intercept? Where, if you were to graph this line, would the line go through the y-axis at?
-5.
-5. That's its y-intercept. That's called slope intercept form. And again, it's a very popular form, especially when you get into applications involving linear equations, of which we're steaming towards. And I'm trying like heck to get there. Hopefully we can get there. All right. Is this making sense how we went from standard to slope intercept form here by solving the equation for y? And I added some extra steps in here that your author's leaving out on your PowerPoint. And like I said, this is being recorded, so you'll be able to see this later on. That's the nice thing about these online courses, is you can watch these recordings at your leisure. It's pretty cool. All right, let's move on here. All right, now, ladies and gentlemen, another way we could graph, this is yet another way of graphing a linear equation. We've seen two ways so far. We've seen the method where you choose values for x and crank out y to, crank out some ordered pair solutions, plot them and put a line through them. We've seen the xy intercept method way of computing the x and y intercept of a linear equation, plotting the points, putting a line through them. Now here's another way. Another way to graph a linear equation is to get it in the slope intercept form, and then being in a slope intercept form, we can read off the slope of the line immediately from the equation. The slope is 5/3, and we can read off the y-intercept. The y-intercept is the point 0, -6. That's enough information, believe it or not, to graph a linear equation. How do we do it? First, we plot the y-intercept, 0, -6, down here. Then, knowing the slope is 5/3, knowing now that we have a ratio of what? 5 units of rise and 3 units of run, we can plot other points on this line. So if I start at my y-intercept 0, -6, if I go up 5 units, up 5 units, and then 3 units to the right, 1, 2, 3, I should be able to plot another point on my line. And there you go. And I can do this again. I could go up 5 again, up 5 units, 3 to the right, I can plot another point on my line. I could do this till the end of time. Up 5 over 3 to the right, plot point. Up 5, 3 to the right, plot point. Up 5, 3 to the right, plot point. Or, ladies and gentlemen, another way I could have done it, instead of going up 5 and 3 to the right, I could have went down 3 and 3 to the left, because 5/3 is equal to -5 over -3. I could have went down 5 units, from a point on my line, and then 3 to the left. And then I would be able to locate another point on my line. Do you agree? So there you go, up 5 and 3 to the right, or down 5 and 3 to the left from one point to another point is up to you. You'll be able to locate points on this line, put a line through the points you plotted, you got the graph. So knowing the slope and the y-intercept of a line is more than enough information to accurately graph the line. So now we have 3 ways of graphing linear equations. All right. Okay. Ladies and gentlemen, there are some special forms here. Whenever your linear equation looks like this, where x is equal to some real number, c, the graph is always going to be a horizontal line. If the linear equation is y equal to some real number where you don't see the x variable, this is always going to be the graph of a vertical line. Okay, these are special cases for linear equations. Now you probably wondered, where's the y variable? Well, it's there. It's just that it's being multiplied by 0. Do you see that there? So it doesn't matter what value you choose for y, x is always going to be equal to that real number c. Similarly, y equals to some real number does have the x variable present. It's just that it's being multiplied by 0. That's why it's not really of any value. No matter what you choose for x, y will always be equal to that real number c. Okay? Those are special cases. So all you have to remember is this. So to graph x equals 5 is pretty simple. It's just gonna be a vertical line that goes through the x-axis at 5. That's all there is to it. Stop and think about why its equation is x equals 5. If I choose 2 different points on this line, the x-coordinate could be anything for these points. I'm sorry, excuse me, the y-coordinate could be anything for these points, but what's the x-coordinate always got to be? For any points on a vertical line, any points on this vertical line, its x-coordinate must always be what? Despite what its y-coordinate is. X-coordinate must always be 5. Isn't that true? That's why it's a vertical line. How about the graph of y equals -3? Well, that must be a horizontal line that goes through the y-axis at -3. It makes sense when you think about choosing 2 unique points on this line. Although the x-coordinates could be different between these points, the y-coordinate has to be -3 for both of them. And that's true for any point on this horizontal line. The x-coordinate, excuse me, the y-coordinate must always be -3. The y-coordinate could be anything. But the x-coordinate could be anything, but the y-coordinate's always stuck at -3. Okay? So those are special cases for linear equations. Okay. All right, hey, we finally made it, ladies and gentlemen, to applying linear equations to the real world. Suppose that the standard fare for a taxi in one city is $5.50 plus 30 cents per mile. Let's try to write a linear equation that basically models this situation of the cost of a cab fare. Then we will use the linear equation to find the cost of a cab fare if we ride for 6 miles, or take an 8.5 mile ride, or a 12-mile ride. Here we go. To model this according to a linear equation, ladies and gentlemen, I'm going to let y be equal to the cost of the cab fare, the total cost. Cost is money. I'm going to let x represent the time that I'm in this cab. Okay. The time of my ride in the cab here. And that's going to be not time. Wrong. It's not time. It should be what? Distance. Sorry about that. Distance. X is the distance that I ride in this cab. They charge me by distance, not time. And the distance will be in what? Miles. Let's see, ladies and gentlemen, if we can write a cost function or an equation that basically relates y to x, cost to distance. Now, we know that the standard fee for just getting into a cab, just getting into one, is $5.50. That's if we drive 20 miles in the cab, or just basically get in the cab and sit in it for 10 minutes. We're going to be paying $5.50 regardless. But there's also a variable cost. This is sometimes called a fixed cost, $5.50. But there's a variable cost, and the variable cost is they're going to charge us 30 cents per mile, where X represents the number of miles. So 30 cents per mile is called a rate, the rate with which we're being charged. They're going to charge us 30 cents per mile times X miles that we drive in this cab. We have a linear equation that embodies this relationship between cost and distance we travel in this cab. Putting this into slope-intercept form, rearranging these terms, I have y is equal to 0.30 times x plus 5.50. This is now in slope-intercept form, this linear equation. Question, ladies and gentlemen, what's the slope of this linear equation? What's the slope? This linear equation is in slope-intercept form. It is in the form of y equal to mx plus b, correct? So what's the slope?
30 cents.
30 cents. Can you explain to me in plain English what this 0.30 is saying in the context of this problem? How do we interpret what it's saying? You're right, the slope is 0.30, but how do we interpret what the slope is saying here in the context of our situation? What does it really represent?
Cost per mile.
Yeah, it's the cost. It's the cost per mile. It's the fact that we're going to be charged 30 cents or 30 hundredths of a dollar for every mile we drive in this cab. It's a rate of change, ladies and gentlemen, of cost per distance. Slope is a rate of change. In this case, rate of change of cost per distance we drive. What's the y-intercept? What would be the y-intercept?
$5.50.
Yep, and the y-intercept represents what? What does that represent? Well, it's what?
It's
the
cost just to get in the cab.
Yeah, it's just the charge, the initial charge is to step into the cab. That means if we drive 0 miles in this cab, ladies and gentlemen, we still have to pay that $5.50. That's a guarantee. If you just step in, you owe $5.50. It's the way it is. Okay, now can I use this linear equation to predict the cost if I drive 6 miles in this cab? How would I do that? How would I determine the cost of going 6 miles in this cab? What would I replace? What variable with 6?
The X.
The X variable. X represents the miles we drive. So I would literally take the 6 down here and I would literally substitute it in for the X variable right here. And then we get on our equation. And the cost Y is going to be 0.30, okay, times 6 plus $5.50 plus $5.50. And what's that going to give us? Well, what is 0.30 or 0.3 or 30 hundredths times 6? I think that's going to be 1.8. Is that correct? $1.80 they're going to charge us for driving 6 miles in this cab, plus the what? The one-time fixed fee of just stepping into the cab of $5.50. Our total fare is going to be $7 and what? 30 cents, I believe. Is that correct? That's the total cost of taking a 6 mile ride in this cab. Everybody see how we did that there? And then you could use that linear equation to predict how much you're going to owe for an 8.5 mile ride by replacing X with 8.5, multiplying it by 0.3 and adding $5.50. And how much is going to cost for a 12 mile ride by replacing X with 12, multiplying that by 0.30 and adding 5.50. Okay. So now we're getting a taste of how we can use linear equations to model everyday situations here. This is just going through the solution I just went through. And these would be the costs, ladies and gentlemen, of taking those rides in the cab. Is this making any sense here? How we modeled that cab situation according to a linear equation. We were able to model it according to a linear equation because the cab fare, in other words, the cost per mile remains the same. If the cab fare kept changing with time or distance, then we would have to be more sophisticated and our equation would be much more complicated. This is just emphasizing the fact that the slope of a line is really the rate of change of Y with respect to X. Here's another one. United States Census Bureau uses demographic information to set a poverty threshold that is used to determine how many Americans are living in poverty based on annual income. For an individual on their own, the poverty threshold was $4,190 in 1980. And it has increased at a rate of $220 per year since then. Wow, that's a hefty increase, $220 per year. Write a linear equation that describes the poverty threshold in dollars in terms of years after 1980. Then use your equation to estimate the poverty threshold value in 2020 and the year that it will pass $15,000 per year. So they want us to take this given data, if you will, or this given information. They want us to develop a linear equation that basically has one variable representing the poverty threshold value versus the other variable, which represents the number of years after the year of 1980. So how would we do all this? Well, let's see here. Well, for one thing, ladies, we're going to let Y be we're gonna let the variable y represent the poverty threshold value, which is dollars. We're gonna let x represent the number of years after the year of 1980. Okay, so what does that mean to let x be the number of years after 1980? If x is equal to 0, what year is it? If x represents the number of years after the year 1980. If x is 0, what year is it?
1981.
No, 1980.
1980.
1980 is x equals 0. Now, if x equals 1, then what year is it? That's 1 year after 1980. Do you agree? That'd be 19 what? 81. Makes sense. If x is equal to 10, what year would it be? That's 10 years after 1980, it'd be 1990. Does this make sense what x represents? It represents the number of years after 1980. Y represents the poverty threshold value in dollars. So let's check this out. At time t equals 0, ladies and gentlemen, well, normally they use t for time, but they're using x in this case. At time x equals 0, which is the year 1980, what was the threshold poverty level value? It was $44,190. Do you agree? That goes right here. Plus, but now wait a minute, it says the poverty threshold value is increasing at a rate, there's the key word, at a rate of $220 per every year. That would be your slope. $220 increase per year. Times x is the number of years after 1980. Does this equation make sense in modeling the poverty threshold value versus the number of years x after 1980? Is this equation making sense here? How we set it up and what it's saying? So what does that 220 represent? That's the slope of this linear equation. You agree this linear equation is in slope-intercept form. Again, it's in the form of y equal to mx plus b form. This is called slope-intercept form. Very popular form for a linear equation. So what's the slope m? 220? What does the slope really mean in the context of this problem? It's the rate of what? Rate of
Change.
the rate of change of the poverty threshold value per how much time? Per, was it 10 years, 20 years, per 30 years, per? No, it's not per 10 years. It's per how many years?
Per year.
Per what?
Per year.
Per year, per 1 year. That's right. So this poverty threshold value has been increasing by $220 per what? Per every year, per every 1 year. That's the slope of this linear equation. The y-intercept would be $4,190. That represents the initial poverty threshold value during the year of 1980. That's the initial value for y when x is equal to 0. And because it occurs when x equals 0, that's the y-intercept of this linear equation. All right, that's the y-intercept. Okay. All right. Now, can we use this equation to predict or to answer this question? Well, they only want us to estimate the poverty threshold value in the year 2020. Well, first of all, what would x be? How many years after 1980 is 2020? Well, if you take 2020 and subtract off 1980, you should get 40, right? 40 years after 1980 is 2020. So now we're going to put a 40 in for x into our linear equation that we developed. Multiply 40 by 220, add to it 4,190. We would predict in the year 2020 for the poverty threshold value to be $12,990. So it's gone from being $4,190 in 1980 up to $12,990 in 2020. Wow, that represents about a tripling in value. Do you agree? The poverty threshold value has tripled in 40 years. To find a year when the threshold value is expected to pass $15,000 per year, we would set y equal to 15,000, not x, but y. because Y represents the poverty threshold value. And now we're gonna have to solve the equation for X to determine how many years after 1980 we would realize $15,000 as being the poverty threshold value. To solve for X, they subtract 4,190 from both sides. They're leaving some steps out again. So they subtracted 4,190 from both sides. Subtract it from the left, 4,190. And when you do that, you get 10,810 equals 220x. Divide both sides by 220. And ladies and gentlemen, we would expect, okay, the poverty threshold value to be $15,000 about 49 years after the year 1980. Well, what year is that? Well, if you add 49 years to 1980, you're going to get the year, which is about what? The year 2029? 2029. We would expect this poverty threshold value to be, reach the $15,000 mark. Any questions how we answered both those questions using our linear equation we developed? Okay, let's see what else we can do. And we're finally done. Okay. All right, ladies and gentlemen, let's go to our textbook and just see if we can do maybe any sort of classwork here today. This is section 6.3. So we learned about linear equations and how to graph them and how to put them in a very useful form called slope-intercept form, and how to interpret what the slope and the y-intercept represent in contextual problems. All right, so in section 6.3, let's see if we can have a little bit of fun now. As always, please do take some time to look down through examples in your section. It only helps to solidify things in your mind as to what occurred here in this lecture. Please do go through and look through the examples. You got the book, it's at your disposal. All it takes is you saying yes to entertain the things we discussed here. All right, let's get on down here. Now, my major emphasis in the time we have left, and we don't have much time left, Liz, is you know how to plot points in the plane. I'm not going to spend any more time with that. I'm interested, ladies and gentlemen, in applications. Okay, I'm going to dive right down here into some applications here. Let's see. Okay, here we go. Number 70, excuse me. A house painter charges $60 for a home visit and $210 per every room that's painted. Write an equation that describes the cost of hiring the painter in terms of the number of rooms painted. Then use your equation to find the cost of painting 5 rooms. Okay. All right, here we go. I want us to let Y to represent the total cost of having this person come to your home and paint some rooms. This is the total cost. And then, ladies and gentlemen, so this will be in dollars. And then I want you to let X represent the number of rooms that are painted. Number of rooms painted. All right, we have arrived at classwork number 1. I want you to develop a linear equation that relates Y to X here. And then I want you to use that linear equation to answer question A here. How much it's going to cost to paint 5 rooms? Go ahead. Classwork number 1. Go ahead and do that problem. All right, so let's try to write this linear equation. It should be, fairly straightforward. All right, so Y, the total cost, is going to be equal to the fixed cost, just having the person come out to your home, is $60. Whether they paint 0 rooms or 1,000 rooms, you got to pay them $60. Plus, ladies and gentlemen, this is the slope. Slope is always rate. So the rate with which they charge us per room. Anything that says per means a rate in mathematics, something per something. 50 miles per hour, 240 words per minute, okay? 30,000 gallons per hour. Those are called rates in mathematics. So they're going to charge us $210 per room. X represents the number of rooms. Putting this in a slope-intercept form, Y is equal to 210x plus 60. Now, to predict how much it's going to cost us for 5 rooms, we let X be 5. Put 5 in for X. Multiply it by 210, add 60 to it. You have the cost for painting 5 rooms. And what's that going to give us? No, 5. Well, it's going to give us a hefty price here. What's that? $1,110? Is that correct? Wait a minute. 0, 0, 11. No, what is that going to be? $1,110. Anybody get that?
That's what I got.
$1,110. Paint 5
Yep.
room. All right, just making sense how we model this according to a linear equation, the situation here. All right, that's classwork 1. Let's see what else we got down in here. Okay. All right, number 73, classwork number 2. It says, according to the technology research company, the Radicati Group in 2021, the average user of a corporate email account received 121 messages per day, and that number increases at a rate of 5 daily messages per year. Write a linear equation describing the average daily number of emails received. Then use your equation to predict how many emails will be received by an average corporate account in 2025 and the year in which the average number of emails will pass $175. Okay, I'll tell you what. The initial year was what? 2021. We're going to let X be equal to the number of what? Years after what year? The number of years after, what's the initial year for this data? 2021, correct? And I want you to represent Y, represent the average number of emails. We'll just say number of emails, okay? All right, go ahead and write a linear equation and try to answer these questions. We'll call this classwork number 2 here. Classwork 2. All right, go ahead. Okay, so X represents the number of years after 2021. Y represents the average daily number of emails received. Therefore, our equation will be Y is equal to 5X plus 121. 121 is the initial number of emails received per day in the year of 2021. It increases at a rate of 5 daily messages per year. To predict how many on average daily email messages are received in the year of 2025, which is 4 years after 2021, we replace X with 4. Multiply, add, you get 140, would expect about 141 daily emails to be received on average in the year of 2025. Anybody get that for that question there?
Yes.
Now, to answer the question, how many years, during what year will we expect the average daily emails received to be 175? To answer that question, we're gonna have to let Y be 175 because Y is the number of emails received. Replace Y in our linear equation was 175. Now we got to solve for X time. So we subtract 121 from both sides, divide both sides by 5, and we get about 11 years. So about the year 2032, the average daily emails received will be about 175. Anybody get that problem? Anybody get that? All right, ladies and gentlemen, that wraps it up. I'm out of time here now. And so we looked at linear equations. We learned how to compute the slope of a linear equation, how to apply them to the real world, how to find X and Y intercepts to graph a linear equation. And so I will make available this homework. I'll open it up on Alex, and as always, try to stay up with the homework, not get behind. That way, that gives you the maximum opportunity to succeed in the course. So I'll stay online for a couple